Hello and welcome. My name is Mark Horseman, Data Evangelist with DATAVERSITY. We would like to thank you for joining the latest installment of the monthly DATAVERSITY webinar series, Analytics Architecture with William McKnight. Today, William's title topic is From Pre-Trained to Fine-Tuned, How to Get the Most Out of Vector RAG and Small Language Models. Just a couple of points to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. For questions, we will be collecting them by the Q&A section. If you'd like to chat with us or chat with each other, we certainly encourage you to do so. And just to note, the Zoom chat defaults to send to just the panelists, but you may absolutely switch that to network with everyone. To find and open the Q&A in the chat sections, you'll see the icons for those features in the bottom middle of your screen. As always, we will send a follow-up email within a couple of business days containing links to the slides, a recording of this session, and any additional information requested throughout the webinar. I just got a note that I might be a little bit quiet. Anybody else in chat having trouble hearing? Um, Now, let me introduce to you our speaker, William McKnight. William has advised many of the world's best known organizations. His strategies form the information management plan for leading companies in numerous industries. He is a prolific author and a popular keynote speaker and trainer. He has performed dozens of benchmarks on leading database, data lakes, streaming, and data integration products. William is the #1 global influencer in data warehousing and master data management, and he leads McKnight Consulting Group, which is thrice placed on the Inc. 5000 list. And for that, I will hand the floor over to William to get today's webinar started. Hello and welcome, my friend.
Hello, welcome everybody. Thank you, Mark. I heard you fine. I hope I'm being heard okay. If not, just come on back in, let me know.
You sound great to me.
Okay. All right. As you kind of pointed out there, Mark, I really keyword stuffed this title. It sort of came together this way. I didn't mean for it to be all full of these keywords, but as I look back as last month when I started to prepare this material, I see that it really was keyword stuff. But I could have gone further with it. I could have included agentic AI and MCP. And this was all the rage this week. I was at the Teradata Possible show, and it was really all about agentic AI. But what we're going to do today is we're going to prepare that foundation for agentic AI by getting our data act together and getting ready with our tools. And these are all tools for the development of AI within the enterprise. And my commitment to you in this series is that if you listen to the last 12 on a rolling basis, that you will have information at the top 1% of this field. And that's how I put these together for you. And you can find all the historical ones on YouTube. And so take it away. All right. These are some of the logos that we're associated with, just to give you a feel for the world that I live in, the place I come from. It's a lot of data movement, operational data and transactional data and analytical data, big data, vector data. Yes, we are a consultancy with deep experience in these tools and strong business acumen. If we can help you out, let me know. And I am really, really proud to say that we are renewed for 2026 here, which I believe will be our 8th year. And that's an eternity in the business of webinars, podcasts, and things of that nature. So I'm really honored to be bringing this back to you next month or next year. So check in every month at this time, second Thursday of the month at this time, and I will have material for you. Here you see what's next year, but I've got, we've got a couple more this year. We're not done with this year yet. And by the way, if you're interested in sponsoring any of these, let Mark know, because that is available as well. Now, the reason we're doing all this is because AI interest is at an all-time high, and it's growing. Simply put, the time it took for ChatGPT to reach 1 million users was very impressive and staggering. We all know this. And it drove everybody across the world to take notice, and certainly enterprises. And that was the fastest growing app of all time. And now we see it in everything that we do. Certainly, if you're pitching an idea to to venture or investment, it needs to have AI in there today. And that's pretty telling in terms of where the world is going. And we've only scratched the surface on what the possibilities are with AI. I believe it was last month I brought to you how to get ROI from AI. And that's the hurdle. It's bridging hype to real world value. So in order to bridge the hype to real world value, we need to learn about the things we're going to learn about today. We need to implement the things we need to implement from today to meet our use cases, meet them successfully, bridge that gap between hype, which of course that's there, but value, which must be there in our enterprise. AI enables an unprecedented level of automation of complex tasks and will drive trillions of dollars in global GDP growth. It's a must-have and a strategic imperative for competitive advantage. And I expect this to be a huge trend next year, along with agentic AI, especially. So we see the budgets coming together now, of course, for next year, and there's AI throughout there. So undoubtedly, you as a data professional, which is who I speak to in this series, is going to be completely impacted by AI, and we'll need to deploy the tools that I'm talking about here today. But keep in mind, the reality is implementing AI can be hard. We've got poor data quality as a challenge, and just access to all data is a challenge. AI agents in particular, they want access to all your data, or I should say, we want to give them access to all our data. That only makes their decisioning a whole lot better. Hallucination still an issue. You need significant computational resources. There's ethical and governance issues. So it's not a drop in the bucket that, we are just going to say the magic word AI and it's going to appear. By the way, though, value is there, as I pointed out last month. You may have heard of this MIT study that's been going around that found that 95% of enterprise AI pilots fail. Sounds pretty scary. And yes, we are at that phase in AI where you're going to get some eyeballs if you talk about it, how it's overhyped and how it's going to fade away and it's a failure and all this. Please ignore that study. Ignore it. It's ridiculous. Pilots are supposed to fail, or at least we should allow for them to fail. They're supposed to be a reach goal, and we're supposed to just learn from them. So ignore that 95% that's been thrown around. That will not help you. It will not help you to dwell on that and get your eyeballs off of the value that can be produced by AI. That's my take on it. Now, the outcomes of using AI, I won't belabor this, but they are many. Increased efficiency, of course. Improved customer experience. We're using AI for that. Enhancing our decision-making capabilities by bringing more data to bear, by bringing it faster to bear on our decisions. Now, largely, the goals of our organizations remain the same, sort of the bottom line. But the methods that we're using to get there can be all these things improved. Improved efficiency, improved customer experience, better decision-making, and so forth, driving cost savings and data-driven insights. So, just really opening up new possibilities. Now, watch out for, though, as we go on, and I won't say this any more today, but it's important that you watch out for AI washing. AI washing, which is this when a vendor will claim AI and it very only is shallow AI at best, or maybe it's just pure analytics. So it's not AI. If it's not AI, it's not going to be as scalable as probably they are proclaiming it to be. And you might think, well, okay, well, you move on. Well, did something happen to you this month? Well, something did happen to me this month, and I'm not in the business of calling out vendors on this series, but I will say, please watch out for AI wash features. Ask questions like, where does machine learning happen in this system, and how does it improve over time with use, which would be a good clue that that's real AI. How much human intervention is required to get results? If it's a lot, maybe it's not AI. And just differentiate real AI, real intelligence from the noise out there. And your considerations are many. Make all that data accessible to AI agents. It looks like MCP is going to give AI agents that context across the enterprise. So that will be something that is required to be added along with AI agents. You'll want to do that. High velocity, fast-paced streaming data is required. So not just straight ETL. You got to get that data moving, streaming in the enterprise. The expectation is that unstructured data will be at parity. Unstructured data at parity. So many organizations now are focused more on their unstructured data than even their structured data. Structured data may be more important per capita, but unstructured data is now where competitive advantage is going to lie. And a lot of this AI, a lot of what we're talking about here today does have to do with unstructured data. So get your data act together. That's my motto. It's the lifeblood of AI agents to give it all the things you see there, contextual relevance, and so on. Now, before we dive into small language models, which are shrunken versions of large language models, let's talk about large language models. So let's get that straight. Now, the history goes back. It goes back. RNNs predicted the next word in a sentence, which is the core of LLMs, right? Back in the early 2000s. And I didn't know that because it didn't hit my world. I wasn't using it for that, but yeah, that's true. It did happen. And in 2017, the Google DeepMind team came out with their paper on transformers. I believe it was called Attention is All You Need. Interesting title, interesting paper, and that kicked it all off. OpenAI then took that ball and ran with it, developed GPT-1. Very interesting origin story around OpenAI. I won't get into it here today, but makes for interesting reading in this space. Traditional programming is instruction-based, but LLM is teaching not how, but giving examples and asking it to learn. It's learning. And after GPT-1, there was BERT, GPT-2, 3. 2020 was a critical point. There was 3.5, 4, and I believe 4 is up to a couple trillion parameters and growing. Multiple models are usually fine-tuned now for use cases where it selects the model and it has multimodality. So these are all getting better. And as I think about companies, who's going to be in that echelon of the top 15 companies in the world in 15 years? Who's going to be there? My guess is, if history repeats, that up to half of them don't even exist today, but they will emerge in this area of LLMs, in this area of GPT, in the areas that we're talking about here today. It's that relevant. So who's going to be the next NVIDIA? Well, I think NVIDIA will be one of those companies, actually, even in 15 years, but who's going to be the other ones? That's worth pondering if you think about trends. Now, large language models, a type of AI model designed to process and understand human language, designed to handle all kinds of data like sequential data, text. We see this in like Siri, Alexa, Google Translate, things like that. LLMs use a transformer-based architecture. Now, it's not exactly a vector database, but it's similar in concept, at least to me, to a vector database where everything gets vectorized and put into hyperdimensional space, and you can see correlations that way. And so when I talk about vector databases a little bit later, it's similar to what these large language models are doing to pull their thing together, right? So images, again, videos, audios, signals. The key components are convolutional layers, activation functions, pooling layers, and then fully connected layers. So lots of examples out there in our world, right? Image recognition, like Google Photos, self-driving cars, medical image analysis, facial recognition, of course, writing. We're seeing all kinds of use for LLMs in writing. So why don't we just hook our enterprises up to one of these LLMs like OpenAI's and use their API, and away we go. Come what may, and just do that and forget about vector databases, forget about small language models, pre-training, fine-tuning, and all that. The expense level of just doing that is prohibitive. to do that. Therefore, most of the use cases that we're seeing out there definitely don't do that. And they're getting into small language models. I'm almost there, but a little bit more on LLMs, because small language models are just shrunken down versions of LLMs. Now, I know if you're super technical, you're going to, debate me on that, and I could debate back on that, but conceptually, this is so. Now, how are LLMs trained? How are they trained? Well, it's a bit of a mystery. They don't like to tell you. There's only a few companies doing it. There's more than there used to be, but it's still, you still got to be a big company to pull this off and scour the web. It is thought that the entire web is pulled into some of these LLMs, books and articles, user-generated content like social media and forums, product reviews, Wikipedia. And the big one that's emerging is synthetic data. Companies are experimenting with using AI-generated data as training material, which it sounds wrong, doesn't it? On the face of it, it sounds wrong. There you see some of the headlines, though, for data guzzling AI companies. The internet is too small. The internet is too small. NVIDIA, Apple, and others allegedly trained AI using 173,000 YouTube videos. Professional creators are frustrated. Yes, professional authors are frustrated. I'm a mini author in the grand scheme of things, but I do know that one of my books is in a data set known as Books 3, which was discovered, and it showed a collection of pirated ebooks that were published in the past 20 years. And those ebooks, it is thought, were used to train LLMs. Since then, I've done a deep analysis of what's in the data set, which is now at the center of several lawsuits brought against Meta and others by writers and content farms like the New York Times and so on. This is going to play out in the courts here over the next few years. I don't expect anything to come of any of it. I don't believe the climate is right now for any sort of how shall I say, barriers to be put up to these companies. These companies are very well connected now, and they've already done this, and it's progress, and I just don't see anything happening. Speaking of synthetic data, before I leave this, it makes up around 70% of the GPT-5 data set. That's how important synthetic data is becoming to these LLMs. So LLMs are ultimately, they're not intelligent. They're persuasive parrots. They're just parroting back what they've seen before. Hopefully what they saw before was good, because that's what we're seeing. As a matter of fact, before I leave that, sorry, for the first time, and I knew it was coming, for the first time, I was on a briefing last week, and I was talking with this vendor about marketing their product. And they were on the subject of marketing how to influence the LLMs. That's right. How to influence the LLMs, because we now largely go to LLMs for information where we used to go to Google and things like that. So yeah, of course, we want to influence the LLMs so that they say good things about our product and so on. So I expect a whole industry to open up with in terms of that. Right? Absolutely. Now, in terms of safeguards, though, I must say there is one that is right there on the table in front of us, and that's the EU AI Act. The European Union, always ahead of the US in terms of regulation. It provides clear explanations. It asks for you to, I should say, provide clear explanations of how the recommendations are generated. And there are massive fines associated with violations. And there's a couple companies that are in the pipeline of possibly being sued for this. And it's a 7% of your global turnover fine, or 35 million euros. So not peanuts, not peanuts. What do we do about this? That we can't go all the way in terms of not being able to explain what it is that AI is doing. And I'm not going to go down that rabbit hole, but if you're talking about this subject, you must bring up the EIAU Act. So what does the LLM do? It tokenizes, which splits the text, let's say text. It splits the text up into words. Now, that's not entirely true. Some words, big words that is, are split even further. And it all depends upon the embedding model in terms of how that all works. But it's split, and that's tokenization, split up, and then embedded into vectors, and then transformed using a multi-head attention algorithm. This tells the model how much words in order is contributing to the sentence as a whole. So it allows the model to capture long-range dependencies and contextual relationships. So it's a mechanism that allows machine learning models to consider multiple relationships between different parts of an input sequence and assign different weights to different parts of the input sequence. And this all means that what comes together as output of the LLM is meaningful. And this is why it can communicate to us in our natural language. Pretty amazing stuff. But it's that basic idea that has just spurned this entire huge industry. How they're trained with that data collection I talked about before, then pre-processing, which can take days to weeks, and then training the model, which can take days to weeks as well. That's very expensive. It uses a lot of electricity, a lot of cooling, and very expensive chips. So NVIDIA chips, largely. And then it scores the words, and sometimes there's human intervention with this. And so I think a lot of us understand how LLMs are trained in a kind of vague way, just kind of to stay there a little bit. A sentence like, the sun was shining brightly in the clear blue sky. So what it will do is it will mask some words like the blank was shining blank in the clear blank sky. And then the LLM tries to predict the missing words based on the context of the sentence. It's like trying to fill in the blanks. The LLM checks its predictions against the original sentence to see how well it did, and therefore it learns, it adjusts and repeats, and the process is repeated millions and billions of times with the LLM playing this fill in the blank game with different sentences and text. And over time, it gets really good at understanding language and generating human-like text. If you've ever been on an LLM, you know that it's speaking pretty clearly. Now, to build an LLM, my point here is, unless you are coming from one of the Magnificent Seven companies, I believe I am trying to discourage you from thinking that you're going to build your own LLM. Now, small language models, that's a different story. I don't really know that you're going to want to do that either, but you can certainly build a vector database of your data, and I'll get to that. But to build an LLM, we may not be doing it, but what they do is they get the data. They need a lot of compute resources. This includes GPUs, perhaps TPUs, that's Google's tensor processing unit. It needs a big cluster. It needs an algorithm. It needs an objective, like mass language modeling. It needs to batch up that data and do it. Models like GPT-4, Claude, and Gemini are creating an unprecedented and rapidly growing demand for electrical power. It must be said, the energy consumption for both training and operating these models is comparable to the monthly power usage of a small city for a single model's training cycle. The energy required for inference is even more. This demand is further amplified by essential cooling infrastructure, where it can increase the total energy consumption by 20% or more. I'm just pointing this out. This surge has ignited a corporate and geopolitical race for energy, with US tech giants investing in private power generation to bypass regulatory hurdles. And the other 700-pound gorilla here is China, of course. And they have more of a state-driven, centralized approach. So it's well worth watching that all play out. And innovations in chip technology and model architecture offer some efficiency gains. They can't fully offset the foundational need for a massive expansion of power generation. Right here in Texas, where I live, it sometimes feels like we're being eaten by data centers. And we'll see how this all plays out. Data centers accounted for around 4.4% of the entire US electricity consumption in 2023, a figure that is projected to grow to between 8% and 10% by 2030. Now, keep in mind, that a data center they're not all the same. There are data centers that house our data. There are data centers that are dedicated to a company like a Google or a Meta to build their LLMs. Those are called AI data centers. And by the way, while I'm at it, there's a third type of big data center, and that's a crypto mining data center. And yeah, I'm not going to get into that, but yeah, those are the data centers that are eating us. Who has built LLMs? Well, you recognize all of these, and there's a few more logos here than the last time that I presented this slide. We've got Anthropic in there, we've got Mistral in there, IBM. There are others. There are others. It's a dynamic field. There's really dozens, and it's hard to keep track of them all. It does require a lot of resources. It's not really an enterprise function, although I would not be surprised if some of the larger enterprises are rolling their own in this arena. There are many LLM use cases. Customer service is a big one, communicating with your customer, advisory, programming assistance, and so on. The Walmart CEO said, "We've used multiple large language models to accurately create or improve over 850 million pieces of data in the catalog." He said, "Without the use of generative AI, this work would have required nearly 100 times the current headcount to complete in the same amount of time." So again, we're not Walmart. Well, maybe we are Walmart, but the idea here is we start with LLMs, but we can't just use LLMs. That would be too expensive. This is, if you want to use LLMs, this is how to use LLMs. And certainly for lower priority, maybe not high use case studies, use cases, you will use LLMs. It's a fine place to start your learning process on this, and it's not that difficult. You do it by API. There's a little code there. Meta's API, for example, this is using theirs for their Llama. You register for an API key, configure API settings, and so on. Work it into your pipelines. You might have pre-processing pipelines where you clean the text, tokenize the data, normalize the data, do a feature extraction, and then post-processing where you format the output, spell check, fluency, re-ranking, and so on. Now let's get to what we're probably going to do more of in the future. And this is certainly a huge trend. First of all, take a look at the paper here that I have on the screen. It's from NVIDIA. Grab that paper, read it some evening when you really feel like it. It's a good paper. And it talks about small language models are the future of agentic AI. A little surprising it comes from NVIDIA that wants you to do everything big, but they couldn't avoid it. Small language models are the future. Now, small language models, they're efficient. You can deploy them faster, lower costs. They have specialized knowledge. They're more easily interpretable. And they have practical application to the enterprises. Now, you can also do, this is an alternative, I guess, to small language models. And this is what led to me doing this presentation, because I realized I was walking around with a decent but not fully developed topology of all this stuff in my head. And sometimes it would fall down when we're on a borderline case. And some of your cases might be borderline. Oh, I could do fine tuning on an LLM, or I could do a small language model. It will be your choice ultimately. But the fine tuning on LLMs is to take raw models and fine tune them for your use cases. And by the way, on all of this, and I'm going to throw another wrench out there, I guess, prompt engineering. Prompt engineering is perhaps most important in all of this. So you can have these great models, but if you don't prompt them properly, try to say that fast, prompt them properly, it's going to be all for naught. Prompting is the new programming, okay? So quickly on fine tuning, it's a technique indeed. And by the way, you could fine tune small language models as well. Most of the time you're going to procure your small language model from a third party like a Hugging Face. That'll be my next slide, so hang on that. But you're going to get that. You might fine tune. Now, fine tuning is going to be more in your camp in the enterprise. Whereas pre-training is going to be more for the originator of the model to do. Okay, so pre-training, we may or may not do it, but we need to know about it. We may do it, but more than likely an enterprise is going to get a pre-trained model and fine-tune it. So fine-tuning is where you're going to take that pre-trained model and adapt it to a specific task or data set. I'll have some more examples as we go along. I couldn't help myself, but get into some of that right now. There are a lot of good applications of small language models, edge AI, mobile AI, real-time processing, IoT devices, and very specialized domains. Now, this kind of brings up the subject of, so do we get one model for multiple uses in the enterprise, or do we get a model for a use case in the enterprise? And then we'll have to get multiple, of course, over the course of time. Most are opting for the latter. I do have a client that is, I won't report back on whether that's a good way or not until I see that play out a little bit more. In my mind, it's kind of like an enterprise data warehouse versus data marts. I'm more geared to, okay, let's get it together and do an enterprise data warehouse. But we're really not going down that path too much. So just to let you know, an enterprise will have multiple of these models. And by the way, just to confuse things, I guess, this is all competitive with a RAG architecture with vector databases in the enterprise. I shouldn't say competitive, it's an alternative approach. So you got your large language models, you got your small language models, or you can roll your own with a vector database with your data. Now, of course, with the small language models and the large language models, unless you build it yourself or you are one of those companies that got to have it all under your firewall, that data stays with the data center, right? We're just API. We're just putting a frame or a filter on. The model is the filter of that data and adapting it to our use case. That's what this is all about, making the model work for your use case. So I'm trying to help you decide which model, which pre-training, which fine-tuning, and well, whether we need a third-party model or whether we're going to build a RAG architecture ourselves. Now, I'd say 75% of the time, at least in my experience in the past year, it's pretty obvious, but it's not always obvious. And that's why we need to know how to distinguish all these things. Belabor that slide. Let me move. Okay, Hugging Face. Hugging Face. My company, we're very keen on Hugging Face. And yeah, we get a lot from there. That's our first go-to place. It may not be yours, and that's fine. But it is a place where it's wide. It has a wide range of pre-trained models and a simple interface for using them. They offer a vast collection of pre-trained models for various tasks, such as language translation, question answering, and text generation. They just specialize in natural language processing and artificial intelligence. So, for example, let's say you choose a pre-trained model, like a BERT or a clinical BERT, which has been trained on large volumes of medical text data. However, you realize that the model may not perform optimally on your specific data set, which contains unique terminology, abbreviations, and formatting. To improve that model's performance, you decide to fine-tune it on your data set. Now, how are you going to do that? We use Hugging Face's Transformers library to load the pre-trained model and then do the fine-tuning. There are tools such as auto-train, fine-tune the model with minimal code and expertise. Yes, there's code involved. Would I or would I not say a data scientist level person should do this? To be safe, yes. Okay, be careful. You can also leverage Hugging Face's Model Hub to explore other pre-trained models and fine-tune them on your data set. And I'll get into fine-tuning a little bit more later. The future of language models, where is all this going? Because we've got to know where that puck is going so that we are ready for it. I see a future of models fact-checking themselves, multimodality, that's already started, improved reasoning ability, bigger context windows, this thing called GPT, it's a research and engineering framework. It's designed to give language models something like a working memory system inspired by human cognition, instead of just relying on an enormous static context window. But context windows are opening up. And the future is, as I mentioned, small language models. Bigger isn't necessarily better. And context beats size. So think that way as you go to market. Now let's talk a little bit more about pre-training and fine-tuning. Pre-training is not normally going to be done by enterprises. At least that's my opinion. Unless you're a really big enterprise and you're doing things that for us normies, we're going to get from a marketplace. Pre-training aims to teach the model general knowledge and language understanding. Both pre-training and fine-tuning aim to improve the model's performance. That's what they're about. So you can get there different ways. You can get more pre-training done or do more fine-tuning. There's more leverage with pre-training, but less control over pre-training, usually. It's okay to think about it like pre-trained happens before an enterprise gets a model, and fine-tuning is done by an enterprise for their use case. Pre-training doesn't teach a model. It evolves it through trial and error and smart curation. Fine-tuning is the art of biasing intelligence. So the intelligence coming out of the language model, okay, that's great. But let's fine-tune, let's bias it to our use case. That's what it involves. It involves taking a pre-trained model, usually a pre-trained model, and adjusting its parameters to fit a specific task or data set. Hugging Face, back to that, it's a popular library for natural language processing that provides a wide range of pre-trained models and fine-tuning tools, kind of a one-stop. You can fine-tune a pre-trained language model to power chatbots that can understand and respond to customer inquiries, which reduces your support tickets and improves customer satisfaction, drives ROI, which is what it's all about, right? You're giving the model the responses you want it to use for certain prompts. So in fine-tuning, you might have a prompt that says, a customer asks, can I return shoes if I've worn them once? Well, how would the model know? How would even a pre-trained model know what you like to do for a return of shoes, let's say your Zappos, if you've worn them once? So you put in your response. You say, that's the prompt. If you get that prompt or anything like it, your response is, our policy allows returns within 30 days for items in new or lightly tried on condition. Shoes should be clean and in their original box. Worn or damaged shoes may not qualify. I'm reading that from my shoe box right here, where I have some shoes to return. But anyway, that's where you give the model your specifics, and you might have 100 of them. Heck, you might have 1,000. Fine-tuning it takes some time, and there are different techniques to fine-tuning. Supervised is the easiest, like in my example, the one I just gave you about the shoes. You teach a pre-trained model to do a specific task by showing it labeled examples. And yes, go no further if you can get away with that. Now, reinforcement learning from human feedback is to improve a model by having humans give feedback on its performance and adjusting it accordingly. So it's saying, hey, what are some of the potential responses that you might have to that shoe inquiry? Let me give a different prompt. Do you ship internationally? Well, again, it depends, right, on your business. So it can say, response A is, yes, we ship worldwide. Shipping times vary by location. So it figures out that might be an answer to, do you ship internationally? Response B is, absolutely, we ship internationally to most countries. You'll see shipping costs at times at checkout. And it might have more responses. And that human feedback can say, I like response A, I like response C, etc. So yeah, that's another way to go about it. Speed things up a little bit, but if you're very particular, you might do more supervised. Now, parameter efficient fine-tuning, I won't belabor these, but this is updating a pre-trained model for a new task without changing most of its underlying knowledge, making it efficient and resource friendly. You can also do prompt engineering, making sure you're using the whole thing in the right way. Self-supervised learning, fine-tuning large-scale AI models requires robust information. This infrastructure includes a distributed computing framework, ML pipelines, and hybrid, potentially hybrid and on-premises, cloud and on-premises deployments. So fine-tuning does not come without resource requirement on your part. Now let's talk about vector databases. This is the roll your own part of it. I'm going to go a little fast here. I gave a whole presentation on just vector databases, but it must be here if you're talking about this subject. Now, people say they have or vendors say they have a vector database. What do they mean? They mean they accommodate the vector data type. So in data types, we've seen a lot of changes over the years, like in NoSQL. Brought us a lot of new data types, and vectors no different in that regard. It's another data type. And it's all about supporting imprecise or similarity search. Have you ever tried searching for something, but you don't quite have the words? Or do you remember some characters in a movie, but you can't remember the name of the movie? Or if you're like me, you can't remember either one. Hey, I'm good at most Jeopardy categories, but not pop culture, okay? In high dimensional space. Remember, some of you will remember tools like Hyperion. That was a cube, 3D. Woo. This is 1000D, okay? In that kind of high dimensional space, vectors that are close to each other show information that is similar. And this adds to a standard keyword search to get more detailed results. I'll have a sample query here in just a bit. So it's a way to get useful results, even if your queries aren't very specific. And let's face it, conversation is not precise. And therefore we need this kind of search. Vector search, there we go. Search based on meaning, not just keywords. So the vector search is the capability of searching based upon meaning. This technique employs multiple machine learning models called encoders to transform text, audio, images, and other types of data into high-dimensional vectors. Vectors are also referred to as embeddings, are essentially a high-dimensional array of numbers. So there's an example, just made it up, just to show you visually what a vector might look like. So imagine a car hunting app that helps customers find cars for sale that are similar to a picture that the customer uploads. Finding a good match requires combining semantic picture search with searches on the data, which includes good old data like location, preference, and budget. And you can do the same with anything. You can vectorize anything. Anything can be vectorized. Any picture, any sentence, any audio, and so on. Like here's some basic examples. The only thing we have to fear is fear itself. It might look like that. Depends on the embedding model. Therefore, you can't tell me I'm wrong because it depends on the embedding model, okay? They're all going to do it a little bit different. To be or not to be, that is the question. I think therefore I am. Okay, they can all get embedded into an array of so many floating point numbers. One per word or one per word breakdown or fragment, okay? Kind of hard to say, but let's say 12 or so floating point numbers for this. Now, therefore, you can glean information because it's numeric, and you can look for closeness because this is stored in hyperdimensional space. So I want to quickly cover what are vectors and what kind of information do you need to understand about them before you can make use of them. That's why I'm talking about vectors being a numeric representation of data. It's an array of floating point numbers. The words that you see there inside of the strings, the letters, everything that's kind of visible there, but the related context are things about that data. The fact that you know the thing is not fear, think is an adjective, and it's not something like blue. I said a lot of words there, but I'm trying to show how it makes meaning out of that sentence. You can imagine that this would be an extremely powerful concept, representing all this information within just kind of a string of numbers. So how do you produce these vectors? You go through an embedding model, which are provided by OpenAI, Cohere, Google Vertex, Hugging Face, several other places. We like Hugging Face, but there are choices here. And so now you might be saying, well, which is the best? Well, I don't know. It depends on your use case. What at this point in time, I don't have a great evaluation model for all the embedding tools. We do trial and error to see which ones are going to work best for a use case, and that's where we are. Maybe the day will come when we'll have better guidance around that. So you send data, whether it's that funky image there or my sentences or whatever, through what's called an embedding, and we end up with our array of floating point numbers, and they exist in hyperdimensional space. Unfortunately, I can't draw a hyperdimensional space. Maybe you can. The best I can do is 2D, arguably 3D, if we want to go there. But as you can see, things are clustered around their cohorts. So we've got some food cluster here. We've got some geography cluster. We've got some animal cluster. Okay, super simplified. But these vectors are produced from similar data that will form clusters in space. It's a simplistic way of looking at what we mean by clustering. And so, I will also just kind of call out here that this is a 2D kind of description of vectors. And what we're really talking about is these very high dimensional vectors. And this is just a way to visualize it, but it's important to remember that we're talking about thousands of connections for these new capabilities that becomes really interesting. Now, one of the models, just to orient you to one of them, is word2vec. Pretty popular, I guess I would say. We like it. It's a technique that represents words as numerical vectors. It has a way of doing things. It's a way for computers to understand what words mean by turning them into the numbers. It looks at tons of text and notices which words tend to appear near each other. So words that show up in similar situations like king and queen or dog and cat, they tend to be closer. And what we're going to do for closeness is we're going to look at that floating point array, and we're going to every number in the array is going to have a difference to the other array, and the combination of all of those differences will say how close things are. So if you're at a party, for example, and you're trying to find who is most similar to me at this party, there's dozens of people there. Well, there's many things that make up you. There is your origin story. There is your what you like to do, your hobbies and whatnot, your education, maybe your career, and so on. So you would go about asking everybody all these questions to find out which one is closest, and your brain would probably explode trying to keep track of it all. Well, that's what a vector database does for you. And databases are adding vector support. Do you need a separate? Is it okay to say DBMS anymore, by the way? I don't see DBMS used anymore. Maybe I should say data lakehouses, okay, to be more relevant. I don't know. But DBMSs, I'll say it, they are adding vector support. Vector data has a wide range of use cases, which are ultimately limited only by your creativity and imagination. Many enterprises are planning to vectorize most of their data and get it in this format so they can do these things. These days, it's for broadly capable platforms that they can have a single interface for, which is why databases, DBMSs, are adding vector support. And so it gives you the best of both worlds. You can do your vector search, and you can combine that with your alphanumeric data that's also in the database. By using the distance between high dimensional vectors, vector search enables us to search through data and find relevant results. Like Billy Edwards here in the picture, he might want to find the closest connection point for his fist and your chin. So that's my bad analogy for the graphics set that I chose for this particular presentation. Let's see if I get on a roll here with it. Maybe there'll be another example here. K nearest neighbor. This is the closest thing we have to an exact search for vectors. So it uses one of the techniques it uses is Euclidean distance. Okay, that's one of the metrics that KNN can use to measure similarity between data points. So it's not an exact search. It offers a powerful approach to data analysis nonetheless. By leveraging the wisdom of its closest neighbors in hyperdimensional space, mind you, KNN unveils valuable insights and predictions in various applications. So this is where, if you're at that part and you're trying to find the people that are similar to you, it's asking all the questions ahead of time. And therefore, when you walk in the party, it says, hey, these are the people that are closest to you. This one also likes the same music you like and is also in the same field you're in. They don't exactly live in your neighborhood, but they're close enough. But they are the closest of everybody here. And so this app will scan everyone else's code and picks the K closest people. The K is characteristics of other people that you want to consider. The more, the longer it's going to take. The fewer, the less time it's going to take. So if you want to just find people that are similar in interest to you in terms of your, what you may do for fitness, what you may do for diet, where you live, it'll stop there. And it'll give you a quicker response that way. And HNSW, now both KNN and HSW, they work together, usually, aim to find the data points in a data set that are most similar to a given query point. It prioritizes speed over perfect accuracy. Pinecone does HNSW the best as far as I can see. They have it's an indexing strategy. And while KNN is an algorithm that finds the nearest neighbors, HNSW is an indexing method for that. And then there are various similarity functions. I started talking about Euclidean. There's also cosine and dot product. I won't belabor that right now. And then RAG is the method for asking questions of the vector database. So if you ask something like, what are the latest breakthroughs in renewable energy? So imagine an LLM as a writer. The vector database is like a giant reference library. RAG helps the writer find relevant books from the library to improve their writing. And LLMs and RAGs, they go together like Jack Haviland here would do a jab cross. How's that? They go together. And so this gives you domain-specific knowledge, contextual understanding, improved accuracy, and vast degrees of customizations. And most vector databases support RAG. LLMs process natural language queries, while vector databases process vector-based queries. And their whole RAG application process looks something like this: document ingestion and pre-processing, vector embeddings, similarity search, and finally passing the top matching chunks to an LLM to generate the answers. Now, we did RAG recently for a benchmark, and coming out of that benchmark, we learned a few things. This was the stack that you needed to do it. This study evaluated an AWS stack against a competitor to compare costs, development complexity, and operational effort. And this is where we are. This is what a lot of companies are doing, stitching together, if you will, some different pieces to do it all. So you got your database and AI, distributed high availability, message queue, your data lake, observability and monitoring, security and compliance. This is the stack that you would deploy to do your RAG. And how would you do that? Well, these are the steps that, if I can get to the next slide, these are the steps that we did. Source document ingestion, document prep, embedding the embedding microservice, LLM generation service, retriever service, the logs, metric dashboard, and alarms. These all took story points, and I won't belabor how, what story points are here and what this means to time and so on, but it comes to a bit of work and some number of months of work to get a good proof of concept, a workable proof of concept into production in an enterprise. And these production story points, by the way, that I show here, show you that it's not over when it goes to production. There's production maintenance cycles, and those are the production story points for 3 years, to give you some context. versus the development story points. So there, you'll still have workaround after you put it in production. This is a simple vector distance function, good old SQL like we know, and the addition of the order by vector distance clause in their predicate, in their order by predicate in there. And this will return results. The closest would be up top. So, and the applications of this are many in an enterprise. Yeah, co-pilots, customer service, IT support, anything that a lot of companies are starting here. They are putting all of their policy documents, their HR documents, if you will, in a RAG architecture, and therefore people can, employees can self-select their way into the policies, and when they have questions, they can ask reasonable questions of that. This is I'm starting the summary now, and the beauty of this, all these slides, I've done too many, but the beauty of having all these slides is in a few days when you get these slides, you can refer back to the slides, especially these summary slides. So I've talked about RAG, I've talked about small language models, fine-tuning and pre-training, and this gives you a little context on what each of them are all about, the model size, the speed, the specialization of them all, and so on. Hopefully I've sorted a little bit of it out for you here today. These are different competing architectures for your use cases. You want to get it right at this level for sure. And then execution of the use case will be obviously very important as well. So use RAG when, use small language models when, and so on. I won't belabor it here. Again, this is for your reading after the webinar once you get these slides. So William talked a lot about RAG and small language models, but when do I use what, when, where, how, and so forth? That's what this is supposed to be. So find your way in here. Also, pre-training and fine-tuning. You're going to mostly look for pre-trained. You're going to mostly look for pre-trained models. So a lot of times you're going to use a small language model that is pre-trained. I would say well over 50% of use cases do that now. You want to use small language models when you have limited computational resources, and don't we all? You need faster inference times, and don't we all? And your specific task requires less complexity than, say, maximum complexity is. You can think it through. Pre-trained LLMs, when you need that state-of-the-art performance on complex tasks, when you can take advantage of more generalized knowledge that might be put onto a model, and you have to understand what that generalized knowledge might be. You also need sufficient computational resources for pre-training if you're doing it yourself, but for fine-tuning as well. In summary, AI is bridging its hype to real-world value. LLMs are trained by exposing neural networks to vast amounts of text data and adjusting their internal weights. In RAG, a vector database, use algorithms like HNSW and KNN for similarity search to efficiently retrieve the most relevant document embeddings. We looked at embeddings, saw what that was. Small language models are lightweight versions of large language models, largely acquired from the same places though, designed to run efficiently on limited hardware, have a vast amount of utility in an enterprise. Pre-training teaches a model general knowledge, and fine-tuning tailors it to a specific task. So if you have specific policies that you want to be conveyed to a customer, you can come up with what those customer questions are likely to be and what the answer should be, and you can put that into the model. And the model, again, is that lens, that frame that we use to look at the data. So this has been from pre-trained to fine-tune, how to get the most out of vector RAG and small language models. Mark, I don't know if I left any time for questions, but now would be that time.
We have a couple of amazing questions in here, but yeah, we don't have a ton of time, so I'm going to try and ask a shorter question. Can graph databases be also used for the development of LLM models? How do graph databases compare with vector databases overall, and which of them can be used for which specific case scenario?
Yeah, that's a good question, because that question has been has been asked before. It's on people's minds. They do serve different purposes. In my mind, it's pretty clear. They serve different purposes in an enterprise. For a vector database, you're going to use that when you have similarity searches. When you're looking for just how shall I say it? Discrete items that are near each other, maybe a smaller use case than otherwise, and small is relative, I know that, but then the graph database might make sense. So I hope that helps. It's hard to say the words for it, but you are right to think that they're sort of in the same boat of category of similarity and closeness, but graph is going to be pretty precise, and vector is going to be where you're allowing for some creativity in the response because you're looking for similarity. You're looking for more of that human language to come out of the whole thing.
Yeah, the adjacency is interesting in vector, isn't it?
Yeah, very.
Cool. Well, thank you so much, William, for this wonderful presentation. Thank you, chat, for being so electric. And I'm sorry we couldn't get to all the questions. You can look forward to a copy of this presentation within a couple of business days. Any parting thoughts before I hit the end button, William?
Go for it. Go for it. Trial and error. Create an environment in your enterprise where you are allowed to experiment, because you want to be ready. You don't want to start from zero when the time comes to implement.
Awesome. Thank you so much. Have a wonderful day, everybody.